So as it was defined in many talks, we can recall that the Riemann zeta function is defined by a product, an infinite product over primes, when the real part of S is bigger than 1. So then you get analytic continuation of this function, and it gives you information on the distribution of primes, for instance, as we've seen in the talk of Dries. So there are many analytic open problems on this function. So first, the interesting region will be what we call the critical strip, which is the region between 0 and 1 for the real part. And we have a functional equation. So understanding just one part, so real part greater than 1/2 is sufficient by the functional equation to get information on the whole strip. And the Riemann hypothesis say that all the zeros of zeta are on this central line. So we see that it's very important to understand the zeta function on vertical lines. So as we've seen in the proof of prime number theorem, the non-vanishing on the one line gives you for free the distribution of primes. So I'm going to focus on this talk to try to get good bounds on the behavior of the zeta function on a fixed vertical line. So it's going to be from the 1/2 line to the 1 line and in the middle. So what is known, what is not known, but what is conjecture? First, it's the Lindelof hypothesis, is that we have a very good control when the imaginary part goes to infinity. We expect a very good control on the zeta function. So as Surya will talk, maybe the bounds of zeta and L functions gives you a lot of arithmetic application. So it's that's why we study it. We study this bound when the conductor goes to infinity. But this is not the order we expect. We have something more precise. If we suppose the Riemann hypothesis, we can actually prove that it's even smaller. Some constant. So if we assume the Riemann hypothesis, we even have a better control on the size of the zeta function. And we can have the same thing, for instance, on the one line. It was first discovered by Littlewood. If now I look at the other edge of the critical strip. Plus some constants. So we have this bound which are conditional. We cannot prove that. We can prove much weaker bounds without assuming anything on the zeros. But we can ask, is it the real order? Can we reach these values? Can we produce values of zeta which match this bound? Can we go up to this bound? So that would be the question. So can we produce values of zeta which match these two bounds? And actually the answer will be no. The bounds coming from the Riemann hypothesis are too big in general. We expect something smaller. But just to say something about another L function, these results we can prove something similar, for instance, for values of L functions, so it gives direct application. So if I denote by KD the Kronecker-Dirichlet character, we have exactly similar bound comings from the Riemann hypothesis for the function, the Dirichlet L function LSKD. So this is just the character associated to the imaginary quadratic extension. So giving upper bounds on the SL function by the analytic class number formula, you get upper bounds on the class number of this imaginary fields. So it's a direct arithmetic consequence of a bound on L function. You have more complicated one, maybe you will talk about that, I don't know. So where these bounds come from? Under Riemann hypothesis, we can in fact, even though the Euler product is only defined for real part bigger than 1, we can approximate the zeta function by a short Euler product under the Riemann hypothesis. So it's the idea how we expect, we make like conjectures, is that we model the zeta function by a short product. So for instance, precisely it means that so 1 plus IT. In fact, if I look on the one line, the zeta function can be approximated by a product which is quite short. So we need only to go to take the first log square primes. So this is conditional on the Riemann hypothesis, but if we assume that, we have an approximation, very good approximation by taking this short Euler product. And from this, you can, for instance, deduce this bound just by applying a prime number theorem. Okay. So now I'm going to state the conjecture about the growth of the zeta function on the strip, and then I'm going to give new results on the one line and try to explain the conjecture on the half line. I'm going to talk about Selberg distribution, central limit theorem. So it's going to be related, I think, to the next talk about Voronin theorem. So the conjecture. So if I take a d-adic interval and I look to the maximum of the zeta function, we conjecture that the maximum okay. So as I said, you see that it's much smaller than the bound that we deduced from Riemann hypothesis. And for inside the critical strip, so we take sigma bigger than, strictly bigger than 1/2. Here we also have a precise conjecture. So I'm not like putting exact constant or so when I put it's log-log, it's an iteration of logarithm. And on the one line, so on the one line we know more precise things. We know, for instance, that it doesn't vanish, so we can really get precise information. We are very close to the convergence region. So let's put it's a long. So here it's the same. Actually, I made a mistake here. We lose a factor 2, but in the constant here. So it's the same here. We kind of lose a factor 2 between the upper bound and what we expect. So this could come from heuristic coming from the short Euler product. So you can make some precise conjecture, and actually here you can prove it. It was proved by Montgomery. So he proved it, but here only for the Riemann zeta function. He proved that we have this, we can produce values. It doesn't prove that it's the maximum, but he proved that we can produce values of this size on this line. And here I prove what it was proved by Levinson, that we can attain also this kind of values. So then I will explain how to refine the conjecture here. But first I will explain how you can conjecture this thing coming from an old theorem of Selberg. So the situation inside the strip is quite well understood since Montgomery, at least for the Riemann zeta function. But on the edges, it remains some open problems. So I will call it justification of the conjecture. So there is an old, very beautiful theorem of Selberg, which says that if I look in a d-adic interval and I make big T going to infinity, actually we know very precisely when T gets big how this values distribute. So we know even better. So this will converge to a normal distribution centered of variance half log T. So what does it say? It says that we have information on the distribution function. So some consequence or rewriting of this is that the measure, we have access to the measure of the T such that, for instance, this zeta function exceeds a specific value when I fix some v. So we have precise information. We know that this behaves like a normal distribution. So we know that this is the size of interval times some exponential, where here you have a variance. So this is for fixed v, and we make t goes to infinity. But we can ask, can we make also v grow with t? So to get much precise information. So if we could do that, v grows with t. What gives you meaningful information? If v grows with t, of course, if v is too big, this doesn't give you any information. But if v goes up to square root of log t log t, you see that this measure estimate is non-trivial up to this bound. So it's kind of say that you can expect that the maximal values of your zeta function should be something like that. You can recover it from Selberg central limit theorem. But we cannot prove that this is true for v which grows up to this kind of values. But we can still prove something. Just for information, Soundararajan. I will write sound because it's always too long to write. Said this is true for v, so it can go up to something which is quite good but doesn't reach the right order of magnitude, what we expect. So it can prove this theorem with v, which grows with t, but not till the values, till the end of the meaningful range. So you cannot deduce this kind. You can deduce good lower bound, but not till the one conjecture. And before erasing that, just a word, just a link to some other famous conjecture, but it will be in the next talk, I guess. If I denote the measure here, let's say by RTV, so it's the t in this interval such that the values exceed with e to v. We have a basic inequality which relates the measure to the moment. So actually, if you want to understand like this distribution of values, you can study this problem of the moment, so the 2k integral on a fixed vertical line, and it will give you information if you understand this object. And this is a well-studied object. We can prove asymptotics, but for k very small. We cannot make k grow without any other assumption. We cannot make k grow very, very big. So, but this we expect that it's something like the length of the interval times some constant times some precise exponent of logarithm. So if we could have a good bound on this, we will have a bound on the large values. Actually, it's what Soundararajan makes. He estimates this set, this measure set, and it gives him like a good bounds on the moments. But always assuming the Riemann hypothesis, so it's unconditional result. So we're not going to prove anything on the half line, so just to give an idea of the conjecture. And here the best results are still quite far. More or less you remove this extra term. The best results, but still quite open, the large values on the half line. So here it's well understood. And here we will refine, like, can we get a more precise, actually asymptotic for the large values. So I'm gonna switch to the half line, to the one line. So on the one line, everything is nice analytically because we have less problem with the zeros as we seen yesterday. Of course, if you move in the center on a half line, you will have like a lot of zeros of a Riemann zeta, and it will cause you a lot of problems in the proof. So on the half line, Granville and Soundararajan, using this idea of short Euler product, we find the conjecture. So how do we do it? As I said, you can see zeta as a product so let's say you fix I don't know, we are on the one line, so we'll just fix here. The thing. So here p to the it is something which go on the unit circle, and for different primes you can expect that this actually behaves randomly. So this is just to p to for every prime and t, it's something which maps to the unit circle, and you can kind of model this by okay, for I take a product of a prime that should be independent, so I can say I will try to get insight on this object by replacing p to the it by some random object. So that's what they do. They define a so identical independent distributed how do you say it? Variables which are distributed on the uniformly on the circle. And if you study so the object you can have good insight about the many things like the moments, the distribution function. And that's what they did, and they conjecture with this kind of ideas. They refine this conjecture, and actually they made the following one. So the conjecture that we can have a second term in the maximum on the line. So we can actually get even bigger values with a second asymptotical term. So they were not able to prove that. They proved something a bit weaker, that we can have this thing which grows what we expect minus some term which goes to infinity. And I will explain how to remove this term and prove this conjecture up to the constant. But still, like the third term of the asymptotic, even if you have good model, it's something very precise. We don't even really know if it's this constant that you could expect. So this, they did it for the zeta function, but for instance, if you look at what I said at the beginning, like L1 KD with, let's say, the d less than certain bound, this is another family of function, and you can still model it here, but instead you will have only, you will model it not by a variable which goes on the circle, but something which takes plus and minus 1 with certain probabilities. More or less 1/2. I mean, 1/2 is going to be 1, it's going to be minus 1. And you can conjecture precise things to the same thing. So instead, for instance, the max over d less than x of L1 KD, you can make similar conjecture here. If I have time, I will talk about it at the end. So what we prove with Aistleitner and Mahatab that the conjecture is true up to the constant. So it's quite elementary proof, so and it can be used in other situations. So I'm going to present the main arguments. So the idea is a very easy analytical idea. If I want to get large values, I can consider these two integrals. I will explain. Let's say we integrate over an R. So I will explain, like we will present a variant of what is called the resonance method. So this function is going to be some function depending only on t, which we call the resonator. And it's going to be constructed in order to extract big values of this. For instance, here I put this theta function, but you could put something else. So how does it work? It works with this very easy analytic principle that the first integral is less than the maximum of your object you're interested in times the second integral. So what you want to do is to construct some function such that the first one divided by the second one is big. So if you are able to do that, you get a lower bound on the maximum of your zeta function. So here I did you have some problem. You have to put some function, some smooth function, and etc. I will go back to that. For instance, some function to localize. If you want to localize between t and big T, of course you cannot just integrate over R. I mean, it will not give you information on this specific interval. So using this method, for instance, you can recover the result of Montgomery inside the strip, what I write at the beginning. So the idea is how to choose well this function. Because of course I put it something, but if you have no idea how you construct this R of t, you won't get interesting information. So because of the structure of a zeta function, historically it was defined, so it was reintroduced by Soundararajan. We defined the resonator by some truncated Dirichlet series. So you truncate up to some big N, and here you put some multiplicative function. So something that you define on the primes and you extend multiplicatively. And the point is then to define well this only a function on the integral to get information. But the point I will explain, you cannot take n as big as you want. You will have some problem. So what was done is that n so I will say small. So you are interested on values of size t, and you can actually, with this method, choose n up to t a bit smaller, t to the 1 minus epsilon. Because in this case, you will be able to asymptotically evaluate exactly E1 and E2. You have an orthogonal system for this n. So I will just show why. Minus plus infinity. Let's say now I will take some smooth function which is a compact support and is more or less taking values between around t, like localizing values around t. And I want to evaluate this thing if I choose r of t on this shape. So what I can develop this, it's going to be a double sum of Rm So let's say I want to control this was my E2 for t big. I get something like that. And of course, when m equals n, I will get like the main part. It's going to be this double sum times the Fourier transform in 0. And why we chose n small, it's because if n small and m is different than n, if you choose well phi such that the Fourier transform decay fast, actually this here what you estimate is just the Fourier transform of t logarithm of m over n. So if m is different than n and smaller than this thing, what is here is bigger than something like t to the epsilon. So if you choose something, some function, some support function which decay fastly, this term is going to be very small for m different than n, and it's not going to go into the asymptotic. So you just have diagonal terms, which are this one, and you can estimate precisely this integral. And you could do the same with the first integral. So then it's just an optimization problem about how to choose well these weights. Yeah. But this gives you big limitation. That's why you cannot prove optimal result. And now I will explain how did we do. So on the one line, we have a good earlier product approximation. So we decided to not choose this resonator as a polynomial, but as a Euler product directly. And then I will define weights for every prime. So as I said, when you are on the one line, something, as I said at the beginning, you can actually here prove that you have you can truncate up to. So what does it mean here is that I take the zeta function in the product. I stop. I take only the first y primes. Let's say you can. So you can prove that, for instance, if you stay a bit away from 0, I don't know. You can actually approximate your zeta function by a short Euler product, and where you stop here will depend on the t, of course. But if you don't assume Riemann hypothesis, you don't approximate with y equals log squared t, but something much bigger, but it's not going to be a problem in our method. So if you want big values of this, you just want big values of short Euler products, and you can work with finite objects. So as I said, we decided to use the structure of Euler product of our zeta to define our resonator as a truncated Euler product. So here you want to basically fix the first, let's say it's not fix the parameter now, first x primes and define it like that with some weight qp for each prime. So what we wanted to do is to take some weight very close to 1 to, if you see the conjecture, I removed it, but like what appears, it's basically with Mertens formula, it's just the product over first prime. I can write it. You want to have something appearing like that, because if you take the product over some first prime here of 1 minus 1 over p to the minus 1, here we can evaluate this as a gamma log x. It's Mertens theorem. So if you can take x big enough, you will have large values if you can relate your large values to this product. If you can, the more the primes you can fix, the bigger you can get values of your zeta function. So that's what we wanted to do. And the question is, like as before, how many primes I can fix. So this idea goes back like to Littlewood. When he produces large values of L function, he did it by fixing the value of the character to the first prime. So he said, okay, I can fix the first log d primes and put that my character equals 1. So everything points on the same direction. So you will expect that you get large values of your L function. And here it's kind of the same idea. How much time do you have? 10 minutes. Okay. So as I said before, the restriction help to produce asymptotics on the two integrals. In our proof, we don't evaluate the integrals E1 and E2 that I define. But we relate the first one to the second one without evaluating them. So we directly get a lower bound of the quotient. So I will explain how. So we had this integral, let's say, was something like that. And now we don't work with the zeta function, but with something, we don't have any more convergent problem or whatever. We just truncate to some parameter. And E2 is going to be the same without the zeta factor. And what we want to do is to lower bound So here we don't have finite series. We have like if we develop in a series, it's going to be a sum over all the integers, which have all their prime factors less than some x. So it's not anymore a series, it's another product. So you can develop it in series. So the first integral, I can write it So as I said, what is that is only a sum with k is y variable, which means that it's p divide k implies p less than some parameter. So I can rewrite this short order product but as a sum over variable integers. So here I can write it as a sum. So this thing. So I just develop this term. And then I have a double sum coming from this. So by multiplicativity, you have an arithmetic function which only depends on the weight you put on the primes. Times this nice function. And as the same, you want to extract some frequencies to get a good understanding of this integral. So here, you can rewrite what appears in the integral part is just m over kn to the it times this nice function. So if you don't want to evaluate exactly these integrals, you can assume more properties on your function here and deduce lower bounds of this I1. So what we assumed is that the function that you put here to smooth has a positive Fourier transform. So if you assume a positive Fourier transform, anything that you see here is positive. So you can remove a lot of terms and just extract some that you're interested in. So for instance, when m equals k to the n, you will have like you can compute it. But when it's different, it doesn't matter if you aim for lower bound because you assume that the Fourier transform is positive. So you can like put it away. Oh, maybe I can let. So that's what you do. Here what you can do is say, okay, for any k that is fixed, what can I do? It takes m a multiple of k. And if you do that by multiplicativity, you will recover the second integral. So only with the structure, you make appear again the integral e2. So you don't need to evaluate. So when k is fixed, you can take m multiple of k, so m k m prime. So what?
Sorry, so are the q's positive? Like those?
What?
Those coefficients are qm.
So these are, you define it for every prime, these are just the multiplicative extensions.
So but like are they positive? Because
What? They're positive, yeah, of course, yeah. You have to assume it, to put it positive, otherwise you cannot use this argument that removing all the time. You will need to evaluate too. So we have this extra condition here. So this, like, I didn't say it. So basically, it's something close to 1 for every prime, so something positive. And I had these integrals of what was there? So if m is a multiple of k, you can rewrite it by k m prime over k n to the it dt, and of course sum of m prime now and n q m q n. So this k will like cancel each other, but we choose the resonator in the multiplicative manner. So if you put m equals k m m prime, qm is just q k m prime by multiplicativity. It's going to be just complete multiplicativity, qk qm prime. So actually here what appears is just qk qm prime. And here you're done, because what is this thing inside the brackets? It's just the second integral. It's just if you develop here, you exactly find this this double sum. So this is only I2. So what you use is like the complete multiplicative structure is very important to make it appear again. So the coefficient are complete multiplicative. So it's for every k, it will give you some coefficient here, and then you recover exactly the same integral. So what does it say? That this thing is bigger than the sum of k times the second integral. So a lower bound is naturally given by the source of this coefficient. So of course I took my truncation of zeta function up to y, but y is going to be much bigger than where you can truncate the resonator x. So this thing is actually is going to be a sum for k x variable. And you recover what I said. If you can choose qk close to 1, this thing is more or less the product for p up to x of 1 minus 1 over p minus 1. What I said in the beginning of the proof. So what you deduce from that is that A1 of the maximum of your zeta function, it's going to be bigger than this product. So here it's like QP close to 1, if you can do it precisely. So if you have that, you deduce that what you're like, I will denote by M, this maximum is going to be bigger than E gamma log x plus some constant. So the point is how many primes I can fix. And you can show that the analytic restriction force you with this method to take x less than log t log t. So you fix the first primes, the first log t primes, and here if you replace, if you make this choice, it gives you exactly this log 2t plus log 3t. . So it means that like you can condition of the first x primes, but you can. It was hidden, but of course I did. You have a by the definition of a resonator, you will have some. You have to control what goes when t goes to infinity. When t is small, you need bonds, individual bonds on the resonator, which limits you to the number of primes you can fix. So this proves like the theorem. And if I have like few minutes, you can actually prove the same for the L function at 1. So if I take Q big, the Q large, and I look at the group of character, a group of Dirichlet character, we can prove that there exists so non-trivial character modulo character modulo Q. So non-trivial character in this group of characters such that the L function in 1 is bigger than something similar so here the conductor is not anymore t, but the values of the modulus of the character. So you can prove similar results for Q large, where exists like you can even have some density results on the number of characters, such that you exceed this kind of values, which beat the previous results where you didn't have you had an extra minus log 4 term. So with exactly the same kind of method, so but instead of this continuous family, like when t varies, here what is which varies like your character, and you will define a resonator, some object which depends on the character, but which makes which reflects the structure. But what we used here is like the integral by choosing a good support function with positive Fourier transform. We had this positive assumption, and here you can replace this by a discrete positivity, which you have from the orthogonality relation. So if you sum over all the character, it's some fixed. If you sum key in xq of key m, this is always positive. It's like it's either the cardinal of a group or 0, depending on the value of A, if it's 1 or not. So instead of having this thing, you will have this km over n to the it. You will have some sum of characters which are always positive, and you just count solution modulo q, and you extract some subset of solution. So you can get the same results, but what is open, which is related to what I say at the beginning, is can you get the same for L1 KID? So if you want, for instance, to get information of the class number of fields, you don't have any more this positivity because you don't have you sum only on real characters. And you can have analog of this orthogonality relation, but it's not exact. You have error terms which makes the method fail here. So we cannot prove it actually for producing large values for real characters, which would be very interesting. So I think I'm gonna stop here.
No, also like so if you just care about primitive characters, right? And then
Yeah.
Then you might not have this sum over primitive characters.
Yeah, you can probably prove it. We did it for prime modulus, but you just exclude the trivial character, and then you will have to bound the contribution of a trivial character, and you will have it will give you the restriction of the size of the primes you can take. For primit, I guess it works too after some manipulation, but we didn't do it precisely.
In the Fourier function, you need a normalization at infinity of the Fourier transform in some sense or not?
We need only positivity for. And you need decay of not the Fourier transform, but the function itself, which previously they needed decay of Fourier transform because they evaluated the integral. We just put a lot of terms away. But yeah, of course, you could try to optimize the choice of the smooth function, but it will impact only the constant term here. I mean, you could optimize really precisely the choice of the weight close to 1, the choice of I don't know where it is, of a support function, but it doesn't give any improvement here. I mean, this is what you expect, so it's only improved, but very slightly, very small improvement on the constant, and so we did some computation, but we didn't really write it down.